So Sarah, take it away.
Okay, yeah, so this is my, this is an abbreviated version of my tenure talk plus some like wild speculations. So, how do neurons, humans, and artificial neural networks predict? I don't think I'm going to be talking a bunch about how artificial neural networks predict, but I will tell you about some experiments with cultured neurons and humans. And the pitch I turn is that started me down that path. So, you guys have heard about what ChatGPT is doing. It solved, I don't know if Paul figured it out, it's doing processes. So, so I always start the talk off with that for students because they use ChatGPT and they want to know what's going on with it. And my claim is that ChatGPT may be very good at prediction, just like the brain is. It may be better at prediction than the brain is. But if you have this x-axis, which is some sense of resources, you can think about how much energy ChatGPT is using. There's no way it's as energy efficient as the brain. So the brain's going to be much closer to this line that separates allowed combinations of resources and predictive capabilities from forbidden combinations of resources and predictive capabilities. And this is like if you're using like 5 kBT to do your computation, you can only achieve some level of predictive power. Or if you're using this much memory, like you're only remembering 5 things, you can only achieve this much level of predictive power. Versus ChatGPT, which basically has like a ton of stuff in it, and they can remember basically everything it's ever seen. So ChatGPT is going to be way over here probably in terms of its resources use, and of course, I think you guys are figuring that out right now, but it could be, very inefficient, basically using a ton of resources but achieving high prediction capabilities, whereas the brain is doing a really job of being what's called efficient. So you can call this resource rational prediction, you can call it efficient prediction, you can call it computational rationality, bounded rationality. But basically the idea is there's this line, it says this is an allowed combination of resources and predictions, some sensor can achieve it. This is a forbidden sensor region, and the brain is going to be really close to the line. Okay, there's my hypothesis. Some people would say, yeah.
Oh, are you sure ChatGPT is actually less efficient than the brain? I think it's pretty efficient. I thought it was pretty efficient.
Which type of efficient?
Well,
like in terms of like watts per like, I don't know, some like per token.
After it's trained, you mean?
After it's trained, yeah.
I would say during training, after that.
Is this after? Yeah, is this inference or like during training?
It depends on what your resources are. I would say I don't know that this is true, right? I've never made this plot with the brain, ChatGPT, and the line. So no, I'm not sure.
Okay.
Show some of these curves, yes.
Huh? Yeah, I will show these curves with the brain, but not ChatGPT.
Okay.
But there's also LSTMs and...
There's a question of which resources, like energetic or how many parameters or something.
Yeah.
So, there's a kink in that curve?
Yes. This is when you have finite statistical complexity, and this is memory. And I'll show some examples of that. But yeah, when you have a finite statistical complexity system, there's like a finite number of bits where you achieve maximal predictive power, and then you just coast. Everything else is a prediction representation.
Okay.
So yeah, that can happen. Okay, so I'll take you through the cultured neurons. I'll take you through the human experiments. I have this in the slides. We'll see how long things are taking. To figure this all out, what we're going to do is we are going to stimulate things with epsilon machines, and we're going to need the epsilon machine framework to figure everything out. And without it, we would just not be able to do these calculations, and we'd have to stick to Gaussian order or Markov stimuli. Which is, by the way, not that bad. This is what some people are doing right now. For whatever reason, it took some physicists a little bit of time to catch up to this, but they're now doing order or Markov Gaussian stuff. We're just going to skip ahead to a completely different class of stimuli, and hopefully the two camps will converge on the same answer. Qualitatively. Okay, you guys know what epsilon machines are. Special type of human Markov model. When I started working with Jim, the whole thing was we're going to get retinal data from Bill Bialik, and then we're going to infer human Markov models of the retinal data in a way that nobody has been able to do so far. And then what happened was I discovered that was really hard, and I was feeling a little bit sad.
Hard to get the data?
No, I got the data from Bill, and then I said, wait a minute, because I took a simple model of a really simple neuron, and I said, what would the epsilon machine of this be? And it would be infinite state. And so I said, this is going to be really difficult because everything that I've seen so far from Jim is inferring finite state stuff. So I was like, okay, I'm kind of giving, I don't really know what to do with that. I had kind of an approach, but it wasn't that great. It ended up being pretty okay, but it wasn't that great when I started. And then I got this paper from Bill with him and Stephanie Palmer, and it totally changed the direction of things. And so basically it just stimulated this entirely new way of thinking about what to do with epsilon machines. So we really understand what the predictive features of epsilon machines are really, really well. So let's just take these epsilon machines, produce stimuli, and send them to some sensor that we care about, some biological sensor, some artificial neural network. And then let's figure out the stimulated thing's predictive properties by looking at how it correlates with the predictive features of the epsilon machine. So that was the basic idea that I came up with because they basically did that for a mass on a spring. Okay. You guys don't need this. This is just, you guys have seen this before from Paul's presentation. You can take a simple non-unifilar hidden Markov model that's just two states, and then if you infer what the epsilon machine of this is, you do this mixed state presentation, you get an infinite number of states. This is very generic, this is very typical. You don't need this. Okay, this is the first slide you don't need. So what we're gonna do is we're gonna say the brain is taking the past of what it sees in this situation where we haven't incorporated actuator stuff, no actions, no behavior. Well, there's behavior in terms of like, but you just see a string of symbols, you don't get to change the string of symbols that you see. It takes that past that symbols, it encodes it somehow in the brain, and then it uses that encoding to make a prediction about the future somehow. So what we're gonna do is we're gonna measure memory on the x-axis in terms of this, essentially a correlation between, a nonlinear correlation between the brain state in the past. We're gonna measure prediction as a nonlinear correlation between the brain state and the future. These can be finite quantities, even though these are infinite objects over here. And of course, you immediately get to the difficulty of how you actually calculate these things. We will get to that completely. You may be wondering, if you know rate distortion theory, why I'm just saying that this is a nonlinear correlation coefficient. It's because there are assumptions in the rate distortion theorem that are just not met. And so I ran this by somebody who actually knows WECS way better than me, and I said, is it okay to be talking about, like, this is just a nonlinear correlation coefficient just by the rate distortion theorem because there isn't an infinite block length? And he said, yeah, there aren't asymptotically large block lengths, you can just pretend it's a nonlinear correlation coefficient. So we're basically just plotting something that looks like a memory on the x-axis and something that looks like a predictive power on the y-axis. This you can mess with, this you can mess with. You can basically imagine other axes that correspond to other resources. You could make this a very high-dimensional plot. Maybe there are even multiple things you're trying to do. There's prediction, there's reward, whatever it is. Okay. But the way we're setting up all these experiments is going to be memory as measured by this nonlinear correlation coefficient on the x-axis, prediction on the y-axis. And the way it's going to shape up is exactly as I showed in the previous diagram. There's an allowed region for combinations of memory and predictive power, forbidden region for combinations of memory and predictive power. And an example of allowed thing might be, oh, you can have 5 bits of memory and use it to make 1 bit of prediction. But data processing inequality says you can't have 1 bit of memory and make 5 bits of prediction. It just doesn't work. So there's definitely this allowed versus forbidden region. The problem is it's really hard to make this curve. We know this point on this curve, this is the causal states, this is the epsilon machine right here. The epsilon machine is the minimal maximum predictive model. So basically, for the maximal amount of prediction, you get the minimal memory, that's the causal states. But you can trace out this entire curve. There's a constrained version of the subjective function. By the way, this is called the predictive information bottleneck. If you mess with this as being the thing you're trying to optimize, it turns into predictive rate distortion. So that's its name. What we're trying to do is we're trying to maximize prediction with the constraint on memory. And by the way, just to foreshadow some results, you may wonder if this has anything to do with actual memory. It does. It turned out to be correlated to working memory in the human task. So I feel kind of okay calling it memory.
How do you measure that?
We'll get to it.
Okay.
Yeah. So there's a separate, so you'd have to talk to Vanessa to see how she measured the working memory, but there's a separate working memory task. Yeah, Alec.
When you maximize over the different probability distributions of R given the past,
Yeah.
are the ones that achieve that upper bound, are they all going to be basically partitions of the past?
Yeah. So there's soft clusterings. So this past has some probability of going to this cluster and some probability of going to this cluster.
Mm-hmm.
That's to be a soft clustering, which is also sort of weird from an information theoretic perspective because soft clusters are not what you want to do to do Watson compression. So this is I could get into the rate distortion theorem and I won't.
Okay.
Yeah, I'm just not gonna get into it because it's just not relevant in my opinion. Okay, so we are trying to maximize predictive power. We're trying to, while there's a constraint on memory. You can turn this constrained objective function into an unconstrained one. You can say, I'm trying to maximize prediction minus some Lagrange multiplier multiplied by memory. And then what you can do is you can basically take partial derivatives that equal to 0. You have an iterative algorithm, you run it. Okay, so but there's a flying ointment that is, I'm dealing with these semi-infinite pasts. So how do I actually operate on semi-infinite pasts? So in order to solve that, Suzanne Still worked with Jimmy Crutchfield and Chris Ellison, and they came up with this idea. Just look at length L pass and length L prime futures. That makes it finite. Hope that L and L prime are big enough. And if L and L prime are big enough, you should reproduce something that seems somewhat reasonable. So what we can do is we can take the even process and we can say, how well are we going to do with the even process? How big do L and L prime have to be? So this is of importance because as L and L prime increase, the number of paths and futures that you have to deal with increases exponentially. So there's recursive dimensionality. Yes?
So I kind of want to go the other way of what's the version of this for finite L? Because maybe we want to be doing something like the mixed state presentation lossy version of that. So what are the kind of optimal belief states given resource constraint, memory constraints,
Yeah.
as you're synchronizing, basically?
Yeah.
So can you still have from the last slide
Yeah.
a similar iterative algorithm
Absolutely.
for the finite L?
There's another
Absolutely.
trick.
Absolutely. Yeah, you can absolutely set up everything just the same way. Just replace the semi-infinite pass with the passive length L, future of length L prime, whatever you want to do.
I guess in a way you're saying that's easier.
It's easier in a
but
way.
but I haven't seen it like in a paper.
It would be, okay, so you can see it in this paper, although I don't know, did you guys write like passive? Yeah, okay. It's in this paper.
Okay.
And I think she used a fancier method than I used in order to actually get these curves, but that's okay. With small L and L prime, small machines, it's not a big deal.
Okay, cool. Thanks.
Okay, so if L and L prime is equal to 2, you get this green curve, 3, 4, 5, and we're trying to asymptote to the right curve because I guess I was interested in experiments where I imagined that they would see a large number of symbols. Okay, so we're trying to get to the right curve. Why is this important? Let's say you have the wrong curve. Let's say that you thought that the green curve was the right curve and the right curve was the purple curve, and you measured the brain to be like right over here. You somehow claim that you had found that the brain was efficiently predicting when it wasn't. So getting the right curve is of like huge importance in order to not make a false positive. Okay, so turns out that the answer is this straight line up and then this straight line over. And the reason you know it is because there's this theorem that says you can replace the semi-infinite past with the 4-time causal state. By the way, if this is going to be a passive length L, it's going to be a finite time causal state, no problem. If you have a future, you can replace it with a reverse time causal state, and you can replace it with a reverse time causal state of finite length, also no problem, if you have a finite length future. And then you get this curve right here because Jim, Chris Ellison, that crew, they developed the technology to get the joint probability distribution of 4-time and reverse time causal states. Okay, so you just get the straight line up.
Quick question about that. So before when you were showing the arc and you mentioned it, the unprecedented equality, I was thinking, well, I would expect it to be a straight line if the unprecedented equality were the limiting case. Like
Yeah, this is weird. This is a weird process. Yeah, let me show you another example. So here's another epsilon machine. It doesn't have this. It has 2 straight lines, but it's not
piece straight linear anyway.
Yeah, it's piece.
So I guess that unprecedented equality is some higher limit.
Yes.
That's a straight line that goes.
Yes. And it's not usually met. Yeah. So you can do this for machine after machine after machine. And there are some tricks that you have to play if you have a generic machine, because what happens is, as you could see from this slide, things explode, so you just kind of coarse grain, but no problem. Okay, so we now have this technology to get these predictive rate distortion curves. This was, I think, a very weird thing at the time that I published it with Jim, because up until then, the idea was to try and just get the causal states, but we're going to use the causal states to get the rate distortion curve. The reason that we were going to do that was for basically doing the Stephanie Palmer bibliographic experiments, and also to coarse grain systems and get like compressed descriptions. Okay, but it was kind of weird, and the reviewers either thought it was a great paper or trash. It was really interesting. So the basic idea was, what was being done before was you had an epsilon machine, you produced data, the data led to recursive dimensionality and calculating these rate distortion curves if that's what you were interested in. Or as we know for entropy rate, and then after the theorem know for rate distortion functions, you can just take the epsilon machine and then you can use this algorithm that has been developed and just straight up calculate this. Okay. So this was the paper that started me on this path. So they took an order 2 Markov Gaussian stimulus. They had a mass on the spring, and it was overdamped, and it was being hit by white noise. And they took a fisheye from a salamander retina, they put it on a multi-electrode array, they measured the responses of a bunch of cells, and they put a visual stimulus that was just a bar moving according to a mass on a string with white noise. And it was just moving up and down, up and down, up and down. And basically their question was, if we look at this binary vector right here that describes how these cells are firing, how well does it predict what happens in the future? How much information does it contain about the past? And if you look at this plot, it's the exact same plot that you saw before. This is memory, this is prediction. They call it I past, I future. They measure in bits. There's an allowed region, there's a forbidden region. They want to know where these neurons lie. So what they did was they chose random groupings of 1, 2, 3, 4, 5, 6, 7 neurons, and they just measured their mutual information using other methods just from the data. And then they plotted that relative to the curve, and it was all in the lossy regime, so it's all the way down here, where everything's basically a straight line. Also, by the way, because it's an order 2 Markov stimulus, they didn't need any of Jim's and mine results that came later. They could just use the Gaussian information bottleneck. And so they found that everything was sort of down here, but it was all very close to the curve. And you see some dots in the forbidden region. You'll see that with some of my graphs too. It's just understandably a non-stationary. It's not, yeah, which is unfortunate, but it is what it is.
They're not reverse time salamanders.
No,
Solid time.
no. But this was very exciting for me. This, I guess, this is mostly for Mike, but basically this was like a version of the efficient coding hypothesis that I really thought was really cool. When I read Horace Barlow's paper about the efficient coding hypothesis, it was kind of like really beautiful text, and then when you looked at the math, it was just like gobbledygook. And so it was really nice to see this like beautifully written down mathematical instantiation of the efficient coding hypothesis for me. So that's where that came from. So we're going to try this for cultured neurons, and we're going to try this for humans, and I'll tell you about what's next, I hope. So for cultured neurons, they took a rat.
Sorry, Sarah.
Yeah.
I was just noting it looked like those salamander neurons were very close to the theoretical limit.
Yeah, that's right.
Is that something you typically expect? Do you think that's...
No. Well, okay, so if you talk to some people, they'll be like, of course things are efficient predictors, and if you talk to other people, they'll say it's a hypothesis you have to test.
Yeah.
And so, I think it's a hypothesis that you have to test, and then after you test it, you figure out how they're close to the line.
Uh-huh.
And so, Stephanie's paper did a really nice job of showing that they were close to the line, and then how they got close to the line was kind of a question mark.
Do you feel like there's been any development in that understanding since then?
Well, we're working on it.
You're working on it.
Yeah.
Okay.
How do you measure how much memory the neurons have?
So what you need to do for this stimulus was she basically said she knew what the position and the velocity of the bar was. So basically you have the past two positions. So you're doing the visual information between the past two positions of the bar and the neural activity from this binary vector. And there's a ton of information estimators that you can use in order to calculate that. So that's sort of like a well-plowed, it's very hard because you have you don't need to estimate the probability distribution in order to actually get an estimate of that mutual information, but it's very hard to figure that out. And people have figured it out, and they have tons of algorithms for it.
And like some neurons just happen to have, like are worse at this task,
Yeah.
like they just have less.
Yeah, randomly chosen groups of neurons, and you can see they sort of dot all over the place. You'll see that with the humans too, they're sort of all over the place.
Okay.
There's not like one universal human performance one on every task.
So it's just like natural variation, like how, and it just so happens that it's very well correlated with like, or like that like it's very well correlated with how much memory they have. The neurons.
Yeah, basically, for whatever reason that we're still trying to figure out, iFuture and iPass are very well correlated and close to this line.
Cool.
Yeah, so that was the first paper. You're now going to see this with cultured neurons. So I worked with Joost and Martino Lamberti at the University of Twente in the Netherlands. Thanks to a very generous grant from Hal Greenwald of the Air Force Office of Scientific Research. And they took rats and they killed them. They put their neurons on this multi-electrode array. You can see the electrodes here, you can see the neurons. And what they would do is they would go through and they would choose an electrode and they would stimulate an electrode that like worked, and it would just hit about 3 or 4 neurons. And those would spread, that activity would spread to the rest of the network. They would also do another preparation where they did optogenetic stuff, and they hit it with light, and they watched it be kind of a noisy light bulb. So in the case that it's just one electrode, you see this is a stimulation electrode. we chose a predetermined set of stimulation times where we knew exactly how they were generated, we understood the epsilon machine, we understood what the predicted features would be. In this particular case, it's just the time since the last electrode hit. And then what you would do is you basically say, okay, if I look at this binary vector that describes this entire population, how well does it understand the future of the stimulation? How well does it understand the past? The former's prediction, the latter's memory. We tried to make it complex. I'll tell you, this is definitely not what I did for my tenure talk because it would have confused the students to high hell. But basically, what we did is we said, well, let's try to make it really complex. Bill, Bialik, Ilya, Neven, and Teletishby had this idea of complexity that came from Peter Grasberger, I guess, in an earlier paper. And sorry, Jim. And basically, it was we're going to try to maximize the mutual information between past and future. And we want that to be infinite, and those processes are complex, and the way you tell how complex those processes are is you look at the mutual information between pasts and futures of length t, and then as t increases, it increases in some way. So it turns out that if you have a fractal renewal process, the predictive information increases as log t, which is a slow rate of growth, but it still goes to infinity. So at first we tried something really close to that. What happened was the mean interspike interval diverges, and you get like you get a stimulation time series that you just can't use. So then we went to something that was way less complex, so I guess it had about 1 bit of excentry. Okay, so this was the results of the paper. They had a way of figuring out their stuff. I'm going to focus on the analysis that fits with this story. So the first thing I want to tell you is they already knew this from doing a lot of experiments. If you look at the functional conductivity before you stimulate and after you stimulate, when you have focal stimulation, so that's stimulation with the electrode, versus global stimulation, which is stimulation with the optics, you see that the functional conductivity really changes when you have electrode stimulation, but when you have the optical stimulation, it basically doesn't change at all. So roughly speaking, what happens is these neurons really learn something when you have the electrode stimulating. When you have the noisy light bulb from the optical stimulation, they basically don't seem to learn anything. Furthermore, if you look into the data, it seems like in the first 6 minutes, really fast, they learn. So the learning happens really quickly. Then if you look, and this lack of learning kind of shows if you look at these efficient prediction plots. You look at how the optical stuff performs. It's about 30% efficient. Getting these lines are still very hard even after the theorem, by the way. So the theorem lets you replace the semi-infinite past with a causal state, a 4-time causal state, and the semi-infinite future with a reverse-time causal state. And we even had what exactly that joint probability density function was. We still had to use David Schwab's NURBS algorithm to get this line in the velocity regime. So it's still very hard to get these algorithms, still very worthwhile to try to come up with ways to get these curves to work out even once you sort of reduce the dimensionality of the problem. So optically, 30% efficient. Electrically, about 80% efficient. 80% is a number that people seem to be just coming up with for randomly different things. So Ben Mokta found that bacteria were about 80% efficient in gathering reward, climbing chemotrophic gradients. I don't know why 80% is showing up so much.
Do you know what maybe I missed it, maybe it's a naive question. Do you know what the solutions look like for the low memory regimes? The optimal ones are the causal states, but what are the
I would direct you to David Schwab's NURBS paper for
okay.
that. So his NURBS paper was basically in the lossy regime, what does this look like? And he gets the line, so you can basically figure out from his paper what's going on.
Okay.
Yeah.
Thanks.
Then they did an experiment where they blocked NMDA receptors, so that's supposed to block spike timing dependent plasticity, and it was still about 80% efficient, which means it must be another learning rule that's responsible for it. Not really sure what's going on. They have some simulations that they're trying to get to reproduce the experimental data, so we can just do knockout experiments and stuff like that with the simulations. Okay, then we did this on humans. So humans were shown a sequence of zeros and ones. They were not shown the epsilon machine, they were just shown the sequence of zeros and ones. So we would show them a 0, they would guess 0 or 1, they would literally have just the 0. So you get 0, 1, say they guessed a 1. We would give them feedback, we would tell them that was correct or incorrect. They would no longer see the 0, they would then just see the 1. And so they get to see basically one symbol at a time. They keep on predicting. And so we gave them 3 tasks. We did not feel like, so the neurons, we wanted to make it really complex, but the humans were like, let's just give them really simple artificial stimuli. We didn't want to have them come in with any like semantic understanding of the stimulus, which is, I think you could do both experiments and it's valuable to do both. One where they do have a semantic understanding of the stimulus and one where they don't. So this is attacking the very artificial stimulus problem. We did noisy periodic. We did something that was called double process by Vanessa Ferdinand, who is the experimental cognitive science on this project. She's from the University of Melbourne, and then the even process with slightly changed probabilities so that if you're in hidden state A, you want to predict 0. Okay, so Vanessa showed, based on these cumulative accuracy scores over a bunch of trials, that for every single one of these experiments, basically by the end of the experiment, everybody was out of the random guessing region, which is just you flip a fair coin and you guess 50% 0, 50% 1. Less true for the even process, but basically everybody's out of this blue region. And then the money shot is this 3rd row here. Instead of doing a mutual information, we just did a predictive accuracy, how accurate were they. And then we did a rate, so this is the memory. Instead of doing, we just did mutual information between the 4-time causal states, the hidden state of the epsilon machine, and their prediction. And you can see the humans are just dotting the curve all over the place. So for the even process and the noisy periodic process, they're basically hugging the curve, these human data. Again, forbidden region from undersampling and non-stationarity. And then double process, they seem to kind of fail. If you look closely at the data in the double process, there's a lot of non-stationarity to the point where by the end of the experiment, most people had not figured out their guessing strategy. They just hadn't figured out how to predict.
I can imagine, I don't know if it's not stationary, but I'm wondering, how do you think about kind of issues that have to do with synchronization, desynchronization?
Yeah, it was, okay, so there was, this was actually a really good example of, you see these 3 dots here? They synchronized so quickly. Basically, as soon as they could synchronize, they synchronized and they guessed correctly. It was almost like they had given the answer key. It was really weird.
Yeah.
Yeah, but most of the time, yeah, we didn't measure like synchronization times or anything like that, which would have been really cool. We happened to be like really slow getting stuff out, unfortunately, because she's in Australia, I guess. Yeah, we didn't measure synchronization times, and we should. And we have the data.
I missed 2, I think, basic things. One is, are you saying you did show them like the process before?
No.
Or you did not?
No.
Okay, so there's not just the inference, but also like learning.
Yeah.
And then the other thing I don't think I caught was how do you measure the memory?
Yeah, so the memory is going to be the mutual information between the hidden state, the 4-time causal state, and their prediction. Obviously, it would be great if we had their brain state, so if we had like an fMRI machine, but this was done during the pandemic, so we didn't have the funding for it. So basically, we just used their behavior as a guide to what their brain was doing. So then it becomes a mutual information between like 2 discrete objects. It's not so bad.
Isn't their predictions correlated to the accuracy though?
Yeah, so the accuracy, so again, okay, so basically the relationship between memory and prediction is you need a certain amount of memory for a certain amount of prediction, but it's possible to have too much memory for that level of prediction. So absolutely, so basically you can get this predictive accuracy from the predictions, and the predictions are going into the memory as well. And so what you can basically say is there's this bottleneck. If they remember the wrong things about the 4-time causal states, they can end up not being close to the curve.
I see.
Yep.
So they can like the wrong type of correlation. Like they can be like inversely correlated, like which is the worst.
Yeah, so for example, like they can remember, like 50% of the time they can remember that they're in like A or something like that, but maybe they should remember that 70% of the time. It's that kind of thing.
Okay. Oh, like for example, if they like always pick the perfect wrong thing, then they would have like very high memory but very low accuracy.
Yeah, that's exactly true.
Yeah.
Exactly true. This is what,
So, sorry, just in terms of understanding the rate on the bottom, that comes from varying the edge probabilities of the particular topology?
Oh no, it doesn't. No, this is the same task showed to all of them.
Okay.
And so what's going on is humans just naturally have different strategies, and their different strategies lead to different values of predictive accuracy and rate.
It's something like mutual information between behavior and the past observation.
That's right.
I see.
Yeah.
Gotcha.
And there was something else I want to say, but yeah.
I'm going back to the thing before, like, it seems like there's two versions of, I don't know if they're both non-stationary, but kind of like that. There's the learning of the task,
Mm-hmm.
where the model of the behavior they're instantiating changes
Yes.
over time.
Yes.
But then there's also the fact that, like, you need to infer where you are
Yeah.
in the
Yeah.
I'm wondering, that second thing in particular.
Yes.
Yeah.
So yeah, so basically, there are some people who acted as though they basically had the perfect model and just need to synchronize. I think for most people, it's a combination of synchronization and learning. I will get into like what we used to try and figure out how they were doing it, which kind of combines both of them at the same time and doesn't really make a differentiation between the two processes. Yeah.
Is this like after they've like they've already did their best to learn it over like many samples? This is like steady
No.
state. Okay.
So this is the second half of the experiment was used to calculate these points.
Second half. So they already had some like learning phase.
Yeah, they had a learning phase which we used to figure out their strategy apparently, and then we used the second half of the experiment to get the data points.
Okay, so the people who are like up there, they could have just learned the model in the first phase,
Yes.
and
absolutely.
now they're just like they're trying to apply the model, so they're just trying to synchronize.
That's exactly right. It
So
just turns out that these points actually appear to synchronize and they appear to have the model down for whatever reason very soon.
Like in the first part of the.
Yeah, in the first part, yeah. If you like look at the data really closely, if you just go into the data.
Oh, but this is the second part, so it doesn't show it. In
Yeah,
this.
it doesn't show it on yeah. So
Okay.
yeah.
Okay.
Yeah.
So this Y scale on each of those, I just can't quite read it. It's not 0 to 1 for each of those pictures, right?
No, it's 0.5 to 1. This is 0.55 to 0.8, and this is 0.45 to 0.5.
Okay, so if anyone was like, I don't know, you had an agent who was trying to guess all of the wrong answers,
Yes,
they would be off of this.
that's right.
Okay, yeah.
So they were all trying, and we gave them some money.
Yeah, of course. And then, so what was the motivation, maybe you said it and I missed it, between, for hiding all of the symbols except the previous one?
Oh, so we didn't want them to use any sort of so this is a mechanical Turk experiment. In
Okay.
theory, if they really wanted to, they could like write down everything they've seen so far on a piece of
Oh, so
paper.
they did have a pen and paper?
But they weren't supposed to. It was supposed to be all implicit. So it was supposed to be just sort of like do you implicitly get how to predict and like
Okay.
what happens to your implicit strategy?
Would it,
Yeah, because I was curious about that, like, if you had any sketch, like, if they were allowed to sketch, because I feel like if you're allowed to sketch,
They
I
weren't
mean, at least
supposed
for
to.
us, we would maybe be able to get it, maybe,
Yeah.
random selection of college students.
Yeah, but we can, yeah, what was the test population?
It was like anybody on mechanical Turk.
Okay.
So, okay, so,
I'm quite amused, but you've got some people who never do better than random. But on the left, bottom there, you have Jim Cramer.
Who?
Well, he's this guy who gives internet stock predictions, and,
Yeah.
and basically, you bet against him, you can do better than
Yeah. So.
Sounds like you've lost some money.
Well,
Oh god, no, he's hilarious. Like,
yeah, one of the common questions that I get when I present this data to people, I don't know if Vanessa gets it too, is basically like, did you look at demographics at all and try to figure out like how that sort of shaped the population? We never did. That would be interesting.
would it actually change the results though if you had people like writing stuff down and just give
I
them
think
like
so.
more memory, right?
I think it would really change. So basically,
But the curve would still be the same, right?
the curve would be the same, but I think that they would start to kick in an explicit prediction scheme instead of just an implicit prediction scheme that sort of like took in the data and just sort of made its best guess using a brain region that's doing implicit prediction stuff.
And people could do explicit guesses just mentally.
I think some like amazing people could. I think for the most part this was implicit stuff.
oh, along those lines, was there a time limit for when they had to?
Oh, that's a really good question. I can't remember. I will get back to you on that.
Yeah, because I'm curious, like, because the motivations for personal mechanical torque, if it's like, were they paid by how accurate they were?
Yeah, if they got like to a certain level of accuracy, they were paid extra. Everybody was paid a certain amount.
Okay, yeah, because it's like then you want to do it as fast as possible, but within an accuracy, you know, what
Yeah.
the
Yeah, I
psychology of that is.
That's a really good question. I can't remember what the time limits were.
Yeah, okay.
Okay, so that was that data. So what we did is we analyzed this. Well, okay, this was basically Vanessa's idea. So she analyzed this data in like a few ways. She basically said, well, first, people in cognitive science would usually just say how accurate were these people, basically how far are they up on the y-axis. And then she said how close are they to the curve is basically our modification of understanding of human psychology. So we're going to calculate how close they are to the curve in some normalized way. And we're going to calculate how far they are up on the y-axis in some normalized way, and then we'll try to compare these tasks. And if you just look at these tasks right here, I think it's sort of by eye apparent that noisy periodic and even process, they were dotting the curve, double process, they were not. So basically, if you just sort of look at it by eye, noisy periodic, they were more efficiently predicting than even process, they were more efficiently predicting the double process. But if you do the stats on it, and you just say, can it predict, well, basically how far up are they on the y-axis if you normalize it, double process and even process look the same. These are the Violin plots that show how the human participants sort out. And when you account for the memory resources, basically how close are they to the curve, you find that it's exactly as you see on those plots. Noisy process is more efficiently predicting than even process is more efficiently predicting than double. So it's sort of a modification of how people were thinking about prediction in our opinion.
What's the vertical axis?
The vertical axis is it's sort of like a normalized distance. So we normalize it so that all the dots over here are at 1, 1. And then we calculated distances from the curve, and we calculated distance up on the y-axis. And so
So higher is bad, or?
yeah, so it was actually a distortion, I think. Let me just look.
I see.
Yeah,
So it's like an error, or?
it's like an error.
Okay.
It's like an error.
Yeah. Sorry, Sarah, I have just another question about like, the model, the experimental setup. So you said they were told whether they got it right or wrong, and they were paid if they hit a certain accuracy. Did you tell them how accurate they were being?
We
Like,
told
they
them
have a
80%
percent?
accuracy.
But did they know like what their percentage was?
They said it was said if they got to 80% accuracy and they were going to paid extra, and then they were going to be asked to do extra trials to just stay there so we could study them.
Yeah. Well, but what I mean is like while they were guessing, other than being told if they were right or wrong, so they kind of had a running tally in their brain.
They knew when they got to the 80% level.
Okay, yeah, I was just curious.
Yeah, they knew. We told
Because
them.
I feel like maybe you would give up. Like if you knew you weren't doing very well and you knew you had to hit this number, but you're not going to do it, you're like, okay, whatever. I just
Yeah.
want to get the payout.
They were being told I don't think they were being told their accuracy the entire time, but you can
That was my good, yeah.
Oh, okay, yeah. But you can sort of pick it up. But yeah, basically they were told when they got to the 80% bar.
Okay, yeah.
Okay, this is where we try to evaluate strategy. So I kind of compare this to blocking STDP and seeing what happens. So in all honesty, this should be a systems identification problem where you sort of say this is the data, what is their strategy? We just did hypothesis testing, so we said maybe they act like order R Markov modelers, Bayesian order R Markov modelers, and they use the last R samples to predict the next one. We said maybe they're actually acting like Bayesian structural inference machines, so they have a bag of epsilon machines and they're just choosing the best one based on the data they've seen so far and using it to predict. Maybe they're acting like LSTMs, so long short-term memory units, state-of-the-art recurrent neural network that looks for long-range correlations, so maybe they're doing that, or maybe they're just doing logistic regression, like something really boring. And so what we did to evaluate this is we looked at what we fed them and what their behavior was, and then we basically said what is the probability of seeing that data given each of these models, and just did a comparison of those probabilities. By the way, the person who validated this method was a really talented undergrad at CMC who's now at the Federal Reserve named Avi Upal. And we ended up with this diagram. So for the noisy periodic process, the order R Markov modelers and the Bayesian structural inference people were about the same. LSTMs are like there was like one person here, 4 people here, or something like that. Most people were n-grams, This is an old diagram, clumpy is actually double. And so this was kind of confirming something that cognitive scientists think, which is that they talk about n-gram learners all the time. This is n-gram. But there are LSTMs, so that's kind of cool. And the Bayesian structural inference was just a nice pop out. Okay.
Wait, Sarah, did you color code the success, like which people on that original plot were each of these?
Oh, that would be a great idea.
Yeah.
That would be a great idea.
I want to know if this, like, if these switching strategies are doing that.
That would be such a good idea. We should totally do that.
Yes.
Is there, we'll see if the reviewers ask for it. Okay. And then I wanted to go towards more complex and just stimuli. So basically, what I want to do is I want to look at the fly brain, and I want to try to use the fly brain to build like a nice recurrent neural network that is efficient prediction. But I'm doing it sort of backwards. So basically, I want to do it from the point of view of here's what the fly sees. Rob D. Stevenik has a really nice movie that he just took of what the fly kind of sees. And then we do a predictive rate distortion curve of that, and we take recurrent neural networks and we feed them different connectomes, and we see how far they get up to the predictive rate distortion curve, and we see which ones win, and then we say, does the brain of the fly look at all like that? So that is the grant proposal it's currently in, and in order to do that, we need these more complicated stimuli. So we've been talking about basically discrete time epsilon machines. Continuous time epsilon machines was a huge part of my graduate work with Jim, and I guess some of the postdoc work too. And you take a model like this where you produce a symbol 2 for a certain amount of time, and you produce a symbol 0 for a certain amount of time, and a 1 for a certain amount of time, and a 3 for a certain amount of time. And you wonder what the epsilon machine of this looks like. It's actually quite complicated, but it's really beautiful mathematically. It's just coupled conveyor belts. So basically, you go along a 0 or a 1 for a certain amount of time, and then you switch to the next conveyor belt after the amount of time of the 1. And then you go up that conveyor belt and you switch to the next conveyor belt. Okay, so basically the idea of this Bulletin of Mathematical Biology paper was to just test this out. And what we wanted to do is we wanted to show the stimuli to things like Hill molecules. We ended up mostly doing it to large random channels, and also Hill molecules. And so you'd see a linear concentration that was like here, and then here, and then here, and then here. And if you looked at the dwell times would have a certain distribution. Okay. These are the things we want to calculate. So again, we're looking at semi-infinite futures. So we're basically saying, what is IPRED? And IPRED in this case is going to be mutual information between the state of the Hill molecule or the state of a large random channel and the entire future of the input. And this is now continuous time stuff. Turns out you can basically write down some coupled partial differential equations and make an estimator of this that really nails stuff. IMM is just mutual information between the current state of the sensor, the current state of the input, and then there's some of the thermodynamic stuff. I was working with Suzanne Still a little bit, and she had developed this idea of thermodynamics of prediction, which Gavin is doing, and I wanted to try it out to see if the bound is good, because basically it's an inequality that says that non-predictive information rate in the continuous time case is less than or equal to the dissipated power, and it's not clear how tight the bound is. The bound is very suggestive. So the bound is basically saying, if you want to be energetically efficient, you have to be predictably efficient as possible, because if you want to make this small, you make this small. So it's a really nice idea. The question to me was always how tight this inequality was, because it wasn't clear to me that it was tight enough to make that statement. So in this project, wanted to compute these things. If you use causal states, you can. We just tested it out on large random sensors, almost as a flex. And then wanted to see what the thermodynamics of prediction bound is at. Okay, so this was the input that we tried for the large random sensors and also for the Hill molecule. Basically, you see it's non-Markovian. You can see there's an extra tau in here and an extra tau in here. If this were just an exponential, this would be a simple Markov process. We just made it slightly non-Markovian. Okay, so it turns out we have this new estimator. If you don't use this estimator, you simulate using the temporal Gillespie algorithm, and you can use then mutual information estimators to calculate whatever you want. And you get closer and closer and closer. Simulation time it gets longer and longer and longer. You get closer and closer and closer as you expect. But basically, you can nail it right away if you use the estimator that we came up with. Okay, so this is what large random channels did. This was the predictive information curve for the semi-Markov stimulus that we chose. And then we did channels that were size 3, size 10, 30, 100, and keeps on going up like that by half order of magnitude. And it just gets farther and farther away from the curve, so it keeps on adopting more and more memory that's just completely useless. So this is an example of I always give this example to students. Basically, it would be like, I have a lot of memory. I'm going to predict the stock price of Apple tomorrow. I'm going to memorize the color of everybody's shirts versus memorizing what the stock price is today. So the smaller channels are actually sort of memorizing the stock price today. These are memorizing the colors of everybody's shirts. Okay, looks like there's a concentration of measure for these large random channels. We find these everywhere whenever we do these problems. Basically what these things are doing is they're just picking up on the symbol so far in order to make their prediction, and then they're picking up on irrelevant parts of the time so far. And the bound, basically, you can see that you get closest to the curve around here, and the bound isn't so tight, but it's tighter later on when they're farther away from the curve. So maybe the efficient predictors are not. It's sort of weird. So the efficient predictors, in this sense, are not efficient in this thermodynamic sense. But this is just one example. Okay, conclusions, culture neurons predict efficiently. Humans predict efficiently except for that one task. They look like their order or Markov modelers. Large range of channels are not efficient predictors. And you can use causal states really well to do all these calculations. Okay, future directions, I kind of told you. I wrote this as, can we use a fly brain to build a more efficient ChatGPT? First, you have to test the fly brain is predicting efficiently, and then import the lessons from the fly brain to AI. So hopefully I get the grant. And then we are having a conversation over dinner. Is ChatGPT intelligent? So I feel like it is kind of intelligent in the ways that people were kind of writing up, and you were writing up some stuff. It was kind of intelligent. At the same time, I'm not going to worry about the ethics of showing ChatGPT a really boring stimulus right now. And I think I'll wait until it's embodied to worry about that kind of stuff.
Why for you is it embodied? Why is it why?
That's a pretty reasonable.
Yeah, I mean.
But morally, why is it important?
I feel like the interaction means that your intelligence really skyrockets to a point where you're kind of more of a physical being that I would appreciate as a reinforcement learner.
But can we already interact with
Isn't it already
ChatGPT?
You can talk to it.
But when you train it, like when you do, oh god, I feel like when you train it, you're just sort of taking an input and doing the next token prediction, and then you're using it to do next token prediction. What I'm talking about more is like they say stuff, and then ChatGPT says stuff, and it like changes what it's trained on. That would be more what I would
Does
call.
that happen to humans? Do humans do that?
Yeah, sure. I mean, we like walk around. I like close my eyes. I don't see anything. I like turn around and I see something different.
Wait, but so you're saying but what ChatGPT says does change what it says later in the context.
That's right. But I want to see it change what it's trained on. So I want to see ChatGPT get out into like social media so much and like various things
No, but for
that its
instance-
training and changes.
No, but for instance, a tiny baby doesn't do this, right? So should we not have 6 month babies?
Oh, no.
Shouldn't they have?
Babies do this absolutely. So like just turning your head means that you change what you see.
Wait, but I still feel like if they say different things, like if you talk ChatGPT, it says different things that influence what it will say in the future.
And it influences what you will say to it.
Yeah. So
Yes, but
it's,
that's like a conversation that doesn't affect its weights. I want its weights to be changed.
Yeah, I don't know, if I think
I
a
don't
lot,
know.
will change what it does
All
in
you're
the
doing is
future too.
moving around in the future.
I don't know.
You're just pushing it around.
So, oh, sorry.
Well, I'm just agreeing with you. Like, you're not fundamentally changing the training set of the model. You're doing
Exactly.
that.
We're just changing the causal state.
Instantiating a particular
Yeah.
generating sequence.
Why should that,
Yeah.
so how does that affect whether or not, as, like if you're concerned about its experience or something?
Yes.
Why does that have any effect on its experience, whether or not it was trained with control of the input or not?
Well, okay. So first of all, it's a completely different like learning paradigm.
It's true.
And I feel like it's closer to an intelligence that I would appreciate as requiring ethical
So
consent.
do you think a cat that's raised in a situation where it's, and they've done experiments with this on visual system cat, it's not able to locomote
Right,
on its own, same visual experience, but where it's not controlling, and then it turns out it changes the way he wanted to,
Right.
but do you really think it changes whether it experiences boredom or not? You know, I don't know.
Yeah, I mean,
I don't
but
believe
that's, but that's different because the cat has the ability to do the interaction. So it's something that has the ability to
So
interact.
the issue is whether there's a capability for the
Yes.
ChatGPT,
And right
not
now it doesn't
whether it's
do that.
implementing its ability.
what about like people who have like can't like form memories or something? Like
Oh, I
It,
mean,
yeah.
they still can absolutely affect like what they see and what
Moment
they
to moment,
experience,
yeah.
and just
but I think ChatGPT can do that too. Like it can't. But I'm saying these people can't like change the weights in their brain. Let's say.
oh, if their connectome is fixed from birth, I think they're kind of dead. So
No,
I
but
don't-
like, what if it's fixed? Like, what if you fix my connectome or something
Yeah,
as
yeah.
it is now? So I couldn't like learn new things or like I
Yeah.
couldn't form new
Sounds pretty
memories.
unethical.
It'd be very ethical, but I still think I'd be worthy of like moral concern. Like I wouldn't want people to like.
It's sad, it's not.
Interesting.
Yeah, I don't think
All
it
the
is.
time. Okay, like
Well, you could probably
I'm not
take
sure.
healthy
I'm not
trees.
sure. That's a
Okay.
really good
Even in the
example.
short
I'm not sure.
depression.
Okay.
You're
I
right.
also wanted to say I think
It's
people
not-
are talking about other resource costs, and I think other resource costs are important to put in, and
Sensory
we really need to figure that stuff out. I mean, this is-
Which resource costs you?
Oh, thermodynamic ones like data efficiency. Like I think people are just throwing around thermodynamics a lot, so I think that's kind of in there. And then I think roughly speaking, what you'd want is something like if you want to study a biophysical system, you'd want like one axis for dissipated work, one axis for material costs, like how how much of this molecule did you use, and stuff like that. And then the y-axis, I would replace prediction with something related to reward, probably, and then make that kind of manifold. And I'm kind of trying to do that, but I kind of use mutual informations instead. And my basic hope is that these mutual informations correlate with the right thing. I'm not sure that they're the be-all and end-all.
Wouldn't you use it as a mechanical experiment with ChatGPT? Wouldn't that be like super easy to do?
Yes, but I feel like I don't want to pay ChatGPT money.
Oh, you can just prompt it money.
Well, you're supposed to tip it, right?
Yeah, it'll perform better.
Okay, well, clearly this is a discussion we should have over drinks.
Yeah.
So I'm gonna keep it going. By the way, this is sort of like maybe what we could have done, but we didn't do. So instead of making it like IMM, we could have made it dissipated power. And then you see an optimal Hill molecule when you don't say prioritize prediction, it has no cooperativity, and then it transitions to a lot of cooperativity. And there are these like local solutions that are not global solutions, and you see the history since it's you around. So I feel like you can get some really interesting behavior out of these vector functions too, just random phase transitions. And I'd like to thank like a ton of people. So a lot of undergrads contributed to this, and they were really talented. And I'd like to thank Vanessa Fernan, Yost, and Martina for doing all the experiments. And I want to thank like a ton of people and like money. And that's all. Yeah.
Thank you.